Hello and welcome to the capstone project of the discrete mathematics specialization. In this project, we are going to design and implement efficient programs for solving the so-called delivery problem. So we start by formally stating this problem. It is formally known as the traveling salesman problem, and the name comes from the following natural application. So imagine n cities and imagine a traveling salesperson in one of these cities. And what he or she would like to do is to visit all the cities, all n cities, and to return back to the initial city. And of course, he or she would like to minimize the total traveling length. Okay? So formally, the input to this problem consists of a complete weighted graph. By saying complete, I mean that there is an edge between every pair of nodes. And by saying weighted, I mean that there is a number on every edge. And this number we call a weight or just the length of this edge. Okay? So a graph may be either directed or not. If it is undirected, then there is just one edge between every pair of nodes. If it is directed, then there is an edge from A to B and an edge from B to A for every pair of nodes A and B. And in general, the weights of these two edges should not be equal. Okay? So what we're looking for is just a cycle that visits every node exactly once and has the minimum total weight or the minimum total length, which is exactly the same. So sometimes in some applications we're interested in finding a cycle, in some applications we're interested in finding a path. So the difference between a cycle and the path is that a cycle starts and ends in exactly the same node, while when we are talking about a path, we mean a path that starts in some node and ends in some different node. So in a cycle, there are exactly n nodes and exactly n edges, while in a path, there are n nodes, and n minus 1 edges. Okay? Okay, now let's focus on this small example. So in this case, we have a non-directed weighted graph, complete undirected weighted graph on 5 nodes. Okay, and we're looking for a cycle that visits every node exactly once. So if you try to find a cycle in this, such a cycle in this graph manually, you will notice quickly that even for this small example, it is not so easy. Okay, so let's consider a few such cycles. For example, if we just go around this graph, we get total length 15. However, if we visit all the nodes in this star shape, then the total length is equal to 11. And it turns out that even 11 is not the best possible in this case. So the best cycle in this case has length 9. Okay, and it is shown now on this slide. So in this case, the total length is computed as follows. It is 1 plus 3 plus 2 plus 1 and finally plus 2. So it is not difficult to see that indeed in this case we visit all the nodes, we visit every node exactly once, and there are exactly 5 edges in this cycle. Okay? So there are just a countless number of applications of the traveling salesman problem in practice, and already in this video we will see several of them. Okay? Then the state of the art is that for this problem we still do not know an provably efficient algorithm. Namely, we do not have any algorithm which is guaranteed to find an optimal cycle in time polynomial in n, for example. So if this is just because we still do not know whether the classes P and NP are equal. So this is a classical NP-hard problem. So we actually do not expect such algorithm to exist. Okay? So in the goal of this project, as I mentioned already, is to implement efficient programs that can solve instances consisting of, say, like 20 or 30 nodes in practice quickly, and that can solve such instances exactly, or such graphs exactly, and that can solve much larger instances approximately. And by saying approximately, I mean that we are going to output not probably an optimal cycle, but a cycle that is guaranteed to be not much worse than an optimal one. Okay? So as for applications, of course the most obvious application comes from delivery problem. when we need to visit several locations to deliver some goods. So this is a problem that is solved probably millions times per day by delivery companies. Okay, so in this case again we have several points and we know all the distances between them, and we would like to visit all of them. So we are interested in it, and probably we're interested in returning back. Right, so we are looking for a cycle, for a travel and salesman person cycle of minimum total length. Okay, so another natural application is the case when we are minimizing not the traveling time or not the traveling distance, but the traveling price. Okay, so imagine that you are going to visit some 5 cities in the US, namely New York City, Miami, Chicago, Seattle, and San Francisco. So what you can, after deciding that you are interested just in these 5 cities, what you may want to do is the following. You first forget about the map completely. So you now have just these 5 cities, and then you figure out what are the prices for flight tickets between every pair of these cities. And in particular, what is shown here is that sometimes the price of traveling from one city to the other one is not equal to the price as it usually happens to the price of flying back, right? So we have 17 here and 15 here. Of course, these are just random numbers that do not reflect the current prices. Okay, so what this example shows is that sometimes we minimize not just the traveling distance or the traveling time, but some different parameter. And in this case, we're actually interested in a directed graph, in a complete directed graph. Okay. So the next application is drilling a circuit board. So imagine a factory that produces circuit boards. A circuit board is something that looks like shown on the slide. So to produce it in an automatic way, they have a machine that drills that drills holes in a circuit board. And of course, the locations of the holes are predefined. So they, for example, look like this. So we would like the machine, for example, a laser, to visit all these places and to drill holes in all of them. And of course, again, we would like the ordering of these locations, of visiting these locations, to be so that the total traveling time between them is as small as possible, right? So, for example, here on the right, we see a potential solution to this problem. So this is probably the shortest such route. Okay, and as you see in real life applications of the travel and salesman problem, there may be like hundreds of nodes to be visited. Okay. Let me also make a remark that an example that we've seen is an instance of the so-called special case called the Euclidean travel and salesman person problem. In this case, we are not given a graph explicitly. We are given just endpoints on the plane specifying just by their coordinates. Okay, and the weights on edges between the corresponding points are given to us implicitly by the well-known formula. So if we have 2 points Pi and Pj, these are just points on the plane, so I assume that this is Pi, this is Pj. So the coordinates of Pi is Ixi, Yy, the coordinates of Pj are Yy, Yj. Okay? Then the distance between Pi or Pj, so the distance in this case is the same as weight or length. So we know how to compute it. This is just square root of the square of it should be xj, I'm sorry, the distance, the square of xi minus xj, and the square of yy minus yj. So we compute the sum of these squares and we compute the square root. So this gives us the distance between the corresponding 2 points implicitly. So it is not part of the input, we can always compute it, right? So, and this is an important special case. So in many applications what we're given is essentially endpoints on a plane, right? And then let me also state some properties. So when we're given such an instance, we're essentially given a non-directed graph, because the distance from pi to pj is exactly the same as the distance between pj and pi. So put it otherwise, the graph in this case is undirected or symmetric. Okay, and what is also important about this special case is that the weights in this case satisfy the triangle inequality. Namely, for every 3 points pi, pj and pk, we know that the weight of the edge from pi to pj is at most the weight of the edge from pi to pk plus the weight of the edge from pk to pj. Namely, put it otherwise, once again, the shortest path from pi to pj is to go directly from pi to pj. Each time when we go through some other vertex pk, we get probably a longer path. So probably there's a path of the same length, but not shorter. Okay. Finally, let me mention the following also application, which is also quite natural. So again, imagine some complex machine, and imagine that there are n mechanical components that needs to be somehow processed or handled by this machine, and all these components are of different types. And we know, so if machine processes some component I and then is going to process some component J, then we need to somehow reconfigure this machine. Or it should be reconfigured somehow automatically, but in any case it takes some amount of time to reconfigure a machine before processing the component J, after processing component I. So in this case, again, we are given some graph. So we know the time needed to reconfigure a machine after processing the component I and before processing the component J. So what we would like to do is the order of processing all our components, which minimizes the total reconfiguration time. Okay, so in the next video we will see one more application, and then we will proceed to designing algorithms and programs for this important combinatorial problem. Our next application is the so-called shortest common superstring problem, abbreviated as SCS. In this case, the input consists of n strings. Okay, and what we would like to find is the shortest possible string that contains each of our n strings as a substring. For example, if we have input strings like BCD, ABC, and CDA, then the shortest common superstring is ABCDA. Right? Indeed, BCD can be found here, ABC can be found here, and CDA can be found here. Right? So this essentially allows us to compress these n strings into one. Right? In particular, if we have many such strings that can be compressed into one string which is not too long, this allows us to store these strings more efficiently and also to use less space. In particular, instead of storing just BCDA, BC, and CDA, we just store the indices of the appearance of the first symbol in the superstring. For example, if the indices they start with 1, then instead of BCD we can store just 2. Right? Instead of ABC we store 1. Instead of CDA we store 3. Okay? So we store just the superstring and the indices of the first symbols. So instead of just 9 symbols, for example, here we store 5 symbols and also 3 indices. So in this case, like the space saving are probably not dramatic, but if we have many such strings, then it makes perfect sense. Okay? So what we've just shown is that there is a natural application in data storage and data compression in this case. But also another famous application of the shortest common superstring problem is genome assembly that we discussed already. So recall that genome is just a very long string, like billions of millions of billions of symbols over the alphabet GT. So, and the story is the current sequencing technologies, they do not allow us to read the whole genome. So what they allow us to read is the short fragments, usually called reads. Okay, so instead of a whole genome, we have many of its relatively short substrings, and that out of these substrings we need to compile a string that contains all the reads. So in reality everything is slightly more complicated because reads contain errors and so on, and we are not interested in a single genome, we are looking for a set of contigs, but still, so the shortest common superstring is considered as a mathematical model for genome assembly. Okay, and at this point it is not at all clear how this particular problem is related to the Trevelyan-Salerson problem, because in this case we have n strings. In case of the Trevelyan-Salerson problem we have a complete graph with weights, but still we will, as you guessed already, it is connected to the Trevelyan-Salerson problem, and we will figure out how it is related just in a few seconds. So as a motivating example, consider the following instance or the following input to the shortest common superstring problem. So the strings ABE, DFA, DAB, CBD, ECA and ACB. First of all, if we're looking for some superstring, not just for the shortest one, then it is quite easy to get one. We just concatenate them, right? So this is just ABA, DFA, DAB, CBD, ECA and ACB. So in a sense we do not compress anything in this case, right? And the reason why sometimes it is possible to compress or to have a shorter superstring is exactly because some pairs of input strings, they have non-zero overlap, okay? So for example, if we have strings ECA and ACB, as you see, they share the suffix of length 1 of the first string, which is A, is the same as prefix of the second string, which is also A. So in this case, they have non-empty overlap. Okay, so A is called an overlap, and usually we're interested to find the largest overlap, the longest one. And this in particular means that instead of concatenating them, we can overlap them, right? Resulting in a string ECA CB, right? Here we can find ECA, it is here, and here we find ACB. So they overlap, and this allows us to save some symbols, okay? And this basically means that what we want to do in this case is to find a permutation of our input strings. That is, we would like just to find an order of these strings such that the sum of consecutive overlaps is as large as possible. And this actually brings us to the idea that this problem is indeed a permutation problem. So what we're looking for is some permutation of the n given strings. For example, if we permute our 6 strings as follows, so DAB becomes the first one, ABA becomes the second one, the third one is ACA, the fourth one is ACB, the fifth one is CBD, and the sixth one is DFA. Then we see that the consecutive strings here, they have overlap 2. Then these two guys have overlap 1, right? One symbol. These two guys have overlap 2, as well as these two guys. Okay, and finally these two guys also have overlap 1, I'm sorry. And this allows us to compress all these strings just in this particular order into one string, which gives us a shorter superstring than what we get if we just concatenate all of them, right? So once again, this brings us to an idea that though it was not obvious from the beginning, but that the shortest common superstring problem is actually a permutation problem. And this, in fact, allows us to reduce this problem to the maximum, to the Trevelyan-Salerson problem, in which we are looking for a path of maximum weight. Okay, so we can argue as follows. So let's construct the so-called overlap graph. So the nodes of our graph are just our input strings, and then we add directed edges between every pair of the strings. Okay, this results in the following graph. So on every edge, so let's just focus on the highlighted edges. For example, on the edge from CBD to DAB, we put weight 1 just because the overlap of CBD and DAB is equal to 1. So indeed, they share the letter D. Okay, on the edge from ACB to CBD we put 2. This just reflects the fact that the overlap from ACB to CBD is equal to 2, just because the suffix CB is equal to the prefix CB of the second string. On the other hand, here we put 0 from DAB to ACB because they do not have any non-trivial overlap. Okay, this gives us a directed graph, and what we would like to find in this graph is a path of maximum total weight. So instead of minimum total weight, as in the classical version of the Trevelyan-Salesman problem, we are looking for a maximum, because the overlap actually tells us how many symbols we can save, right? And we would like to save as many symbols as possible. So instead of finding the minimum weight path, we are looking for a maximum weight path. In almost all approaches that we are going to consider in this class, actually it doesn't matter whether we are looking for a minimum path or for a maximum. And also this illustrates nicely that sometimes we're interested in a minimum path, sometimes we're interested in a maximum path. Okay, so that's why we have prefix max for this problem, just to emphasize the fact that we are looking for the most heavy path. And also this letter A here stands for asymmetric. Okay, this means that we have a directed graph. So you can find such abbreviation in the literature. So the Trevelyan-Salesman problem is just a general version. And if you would like to specify that you are looking for a longest path and not in the directed graph, then you specify that it is a TSP. Okay, so finally, when we construct such a graph and we find a path of maximum weight, this gives us something like this. Okay, so this is a path of maximum weight in this particular graph. So it goes as follows. So it visits all the nodes. Then this path actually spells a superstring that is as short as possible. So we kind of start with DAB, right? This is DAB. Then we go to the next edge, to the next node. I'm sorry. We see that there is an overlap of size 2, so which means that we already have AB, right? So we add just E to this string. Okay, then from ABE we go to ECA, and we know that the overlap is equal to 1, which means that we just append CA. Okay, just instead of appending 3 symbols, we append 3 minus 1 symbols just, and so on. So by going through all this along this path, we spell a superstring of all our n strings. And the fact that this is a maximal path guarantees that what we get is a superstring that saves as many symbols as possible, which in turn means that this is the shortest common superstring. We now turn to considering various approaches for solving the Trevelyan-Salesman problem. As usual, we start with probably the most naive possible approach. Okay, so namely, we're going to consider an approach that just enumerates all possible candidate solutions and among all of them selects the best one. This is known as a brute force search, or a brute force approach. So first of all, let's try to understand what is our set of all candidate solutions. So what I claim is that what we're looking for is more or less a permutation of our n given nodes. So why am I saying more or less? Well, let's see. Assume that we have just four nodes. Indeed, what we need to, so I'm drawing only the nodes of our graph, but at the same time we have all possible edges between them, and assume that our graph is directed, for example. So what we need to find is actually an order of visiting these nodes. For one such order is, for example, BDCA. This corresponds to the following. So this is a permutation, right? And of course it defines a cycle. So from B we go to D, from D we go to C, from C we go to A, and then we return back to B, I'm sorry, because this is the first element of our permutation. At the same time, this correspondence is not one-to-one. Namely, in our permutation there is a first element, of course, B, while in a cycle there is no first element, right? So this actually means that for one cycle there are n different permutations, where n is the number of nodes. Namely, there are n different permutations which give the same cycle. So, for example, the permutation DCAB also gives rise to the cycle shown here on the slide. And also CABD and of course ABDC. So they all give the same cycle because they basically correspond to the, for example, DCAB is like a cycle, is the same cycle where we start from the vertex D, from the node D. Okay? So, but still, roughly, when we're looking for a cycle, we're looking for a permutation. Okay? Or for a permutation with some first node fixed. This basically tells us that the number of different cycles is n minus 1 factorial. So n factorial is the number of all permutations of n objects, but because we can assume that the first node is fixed, right? So if the first node is fixed, then for the second node there are n minus 1 choices, for the next one there are n minus 2 choices, for the next one there are n minus 3 choices, and so on. So the total number of cycles, of different cycles, is n minus 1 factorial, which is almost the same as n factorial. Okay? And unfortunately, the n factorial function grows extremely fast. Okay, so just to show you how it looks like, note that, for example, n factorial when n is equal to 5 is equal to roughly 100. So this is, let me just remind you, this is just 2 times 3, which is 6 times 4, which is 24, and times 5, which finally gives you 120. Okay, this is a reasonable number. I mean, we can definitely implement a program that goes through 100 possible solutions and does this very quickly. However, when n grows, n factorials gets longer and longer and longer. For example, already when n is equal to 20, 20 factorial looks like this, so definitely more than 10 decimal digits. And when n is equal to 30, n factorial is a huge number. So definitely our modern laptops are not able to perform so many operations per second, not even per second. I'm not saying, and even not in an hour or even not in 1 year. So an algorithm working for n factorial operations is not going to be practical even for n equal to 30, unfortunately. So this also tells us that the search space in case of the travel and salesman problem is huge. It is impossible to explore the whole search space to find the best solution. Okay, so, and this tells us that we definitely need some smarter approaches. But before going into such approaches, let's explore also the following idea. We've just realized that it is not affordable to go through all possible permutations. But what about just selecting the random permutation? Let's just pick a random permutation out of all possible permutations and hope that it is going to give a not so long cycle. So unfortunately, it turns out that the length of a random permutation may be much worse than the length of the best permutation, even if we consider a special case of Euclidean TSP. So as I mentioned already, in case of Euclidean TSP, sometimes solving such instances is easier, in particular because they satisfy this triangle inequality. Okay, and it is not actually too difficult to understand why it can be that bad, but it can also be shown formally. So the lemma that you see here on the slide actually tells us that tells us how to compute the weight of a random permutation. And when I say the weight, I mean of course the expected weight. Okay, so the expected weight of a random permutation is equal just to the sum of the weights of all edges divided by n minus 1. And here I assume that we have a directed graph. Okay, so informally, this can be proved as follows. So in a cycle, we have something like, we have exactly n edges. And in a complete directed graph, we have n times n minus 1 edges. And since everything is symmetric, each edge has probability 1 over n minus 1 to be included into a random cycle. Okay? And then, which means that for each edge, its contribution to the expected length is its weight divided by n minus 1. Okay? So in this, since the expectation is linear, we can compute the total weight as the sum of expectations of all the edges, which gives us the sum of all edges divided by n minus 1. If you would like a more formal proof, you can argue as follows. The total number of different cycles, as we've discussed, is n factorial, right? Is n minus 1 factorial, I'm sorry. Now let's do the following. Let's fix a particular edge, for example UV, and let's count the number of cycles that contain this particular edge. Okay? Since, as you remember, since we have a cycle, we are free to select its starting point. So let's just assume that so we have a cycle and we are counting the number of edges, the number of cycles that contain the edge, I'm sorry, UV. So let's assume that U is the starting point of this cycle. And since it has Vertex V here, we know that there is U and V here. And for all the remaining edges, for all the remaining nodes, I'm sorry, we are free to select any particular permutation. So any of n minus 2 nodes here, any of n minus 3 nodes here, and so on. So the total number of permutations that contain this the total number of cycles, I'm sorry, that contain this particular edge is n minus 2 factorial. So the fraction of all cycles containing a particular edge is actually 1 over n minus 1, and this is also a probability of a fixed edge to be included into a random cycle. Okay, and this, let me erase now everything and let's discuss this. This means that if in our graph we have some very heavy edge, then it will give the contribution to a random permutation also, right? Its weight will give a contribution to the weight of a random permutation, and this is something that we would like to avoid. Because probably there are many heavy edges in our graph, but what we're looking for is some cycle that avoids all the heavy edges, right? Probably a more interesting example is the following. So consider just this simple data set. So we have some bunch of points here at the bottom left corner and some bunch of points here at the top right corner. So of course, for this particular example, it is not so difficult to convince yourself that the best cycle looks like this, right? So we first need to somehow traverse all the nodes here at this corner, then we go to the opposite corner and traverse all the nodes here, and then we go back. Namely, so there are two groups of points in at different corners, and it makes sense, of course, to go only once from one corner to that corner and then to return back. Okay, but if you consider random permutation, then it will look like this. So it will take too many long edges, and that's exactly why a random permutation may be much worse than the optimal one. Okay, so in the next videos we are going to consider smarter approaches for solving the Trell-Seligson problem. In particular, we will start with an approach that can easily solve this particular data set. And you've probably guessed already, so there is a very reasonable heuristic to solve this particular one. So from each node, let's go to the nearest node which hasn't been visited yet, right? So this will solve this particular data set immediately, right? Because from starting from that node, we will go to that one, then to that one, to that one, then to that one. Then the next unvisited node is this one, I mean the closest one. This will lead us here, 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 and finally here. So in a sense, this data set is not so difficult to solve in practice. So in the next video, we are going to explore this approach further. In this video, we are going to discuss the so-called nearest neighbor approach, or it is also sometimes called a nearest neighbor heuristic. Okay? As we've seen, just pulling a random permutation, pulling a random candidate solution might give quite poor result. At the same time, for the input data for which this heuristic of taking a random permutation gives a bad result, we've seen a very reasonable approach that produces an optimal solution and does this very quickly. Namely, we start at some node, and at every iteration we try to visit the node which is as close, which has not been yet visited so far, and it is the closest such node, right? So first of all, the good news about this heuristic is that it can be implemented very efficiently, right? We do not need to explore the whole search space, which consists of roughly n-1 factorial permutations, but just at every iteration we need to find the closest node, which kind of at every iteration we need to scan through all possible neighbors. So we definitely can implement everything just in roughly n squared steps, right? So it is efficient, and in many cases, particularly for Euclidean TSP, in practice it produces quite a reasonable result. So we are not guaranteed to find an optimal solution using this heuristic, of course. So let me remind you, we do not have any polynomial time algorithms for the travel and salesman problem, and this algorithm is definitely polynomial, so it works in time in n squared, so in polynomial time. At the same time, it produces solutions that are in practice usually are not much worse than an optimal solution. Okay? So for general graphs, not for Euclidean instances, but for general graphs, it unfortunately may produce a solution which is much worse than an optimal one, and we will see such an example in a minute. For Euclidean TSP, it usually works better, but still it can produce a cycle which is roughly logarithm of n times worse than the optimal one. So for example, when n is equal to 1000, it will produce a solution which is 10 times longer than an optimal one. Okay, so first of all, let's discuss how would you fool this heuristic or this approach for the case of general graphs, right? So to produce such an example, assume that we were given a graph where almost every edge have weight 2. At the same time, there are some edges that have weight 1. So assume that there are just 5 edges, and again, almost all of the edges have weight 2. At the same time, there is an edge of weight 1. So we start from some node and we start constructing our cycle. So we go to that vertex, and it turns out that from this vertex or from this node there is another edge whose weight is also 1, which is good for us, right? Because we know that almost all other edges have weight 2. Then we find another edge, but at this point we already have no choice. Right? We need to go to the only unvisited node, and if we're lucky enough, this edge still have weight 1, but for the last edge we have absolutely no choice, as for the previous one actually, and it might turn out that its edge is just so huge that it just doesn't pay out to use all these ones, right? So in this case, and this is a situation, one of the situations where the solution returned by this approach might be poor. Okay, so recall also that it might as well be the case that the weight of this edge is also huge. It is something like, I don't know, 10 to the 6. So we make some greedy choices at the beginning, but it gives us no choice in the end, and we need to take this last very heavy edge. Okay, but of course this cannot happen for the case of Euclidean TSP. I mean exactly this picture, because if we assume that almost all the edges have weight 2, then for example we should have an edge of weight 2 here, an edge of weight 2 here, an edge of weight 2 here, and an edge of weight 2 here. But this would mean that an edge from this node to this node should have weight at most 8, right? Just because it is a Euclidean graph, and in this case, just by triangle inequality, we know that if we go like this, this, and this, it should not be longer. It should not be shorter, I'm sorry, than just going directly from this node to this node. Okay, but as we've mentioned already, even for Euclidean instances, or for the Euclidean TSP, this heuristic might produce a suboptimal result. And let me just show you some small examples. So if we have these 4 points on the plane, then the optimal way of visiting all of them is shown here on the slide, and its length is roughly 26.42. Okay, so we assume that the length of this in this grid is equal to 1. So for example, the length of this edge is something like 2 squared plus 3 squared and square root of this. Okay, so if you compute carefully the sum of all four edges shown here on the slide, you will get something like 26. At the same time, if we start to construct a solution greedily using our nearest neighbor heuristic, it will give us the following cycle. So assume that we start at this node, then the closest one is that one. Okay, so we go to this node. Then from this node we go to that node. So it happens that this one is closer than the only remaining one. Then we go here and we go here, and it gives a solution whose total length is 28. The difference is small, but still. So first of all, this is an example where this heuristic produces a suboptimal result. There are other examples where this heuristic, even for Euclidean TSP, produces a much worse result than an optimal one. And still, let me remind you that in practice this heuristic works quite well. So if you are okay that your fast algorithm is going to produce you a result which is probably not optimal, but at the same time not much worse than an optimal one, then this could be a reasonable choice in practice. Okay, in the next videos we are going to consider algorithms that are guaranteed to compute optimal result, but at a cost, of course, at a longer running time. The branch and bound technique allows to solve the TSP instances exactly in practice. That is, the branch and bound algorithm is guaranteed to output the best that is optimal solution. The only issue is that it is not guaranteed to have low running time. That is, on some instances it is quick, on some instances it is slow. Its main idea is the following. Assume that we were just enumerating all possible cycles, or all possible permutations. How would we do this? So we start with some node. Then we know that from this node we can go to either this node or that node or that node, so n-1 other nodes. From each of these nodes we can go to either this one or this one or this one. So we construct like recursively these tree of all permutations. At the same time, for some branches of the tree, we can cut them somewhere in the middle, just because we already know that this branch or this current subpath cannot be extended to an optimal solution. And this is best illustrated with an example. So just consider this small graph with 4 nodes, and this is how the whole tree of all permutation looks like. So from the node, we start with node 1. Okay, from 1 we can go to either 2, 3 or 4. Okay, from the node 2 we can go either to 3 or 4, just because we do not go to 1 because 1 is already visited. Similarly, from node 3 we can go either to 2 or to 4. Okay, from the node 4 we can go to either 2 or 3. Again, because 1 is already visited. Okay, then from 3 we have already no choice, we need to go to 4 and then to go back to 1 and so on. So the leaves of this tree correspond to all possible permutations. And actually from all possible permutations starting with 1, and you see that 7 is the best length of a cycle. So the best cycle in this case is, let me draw it on our toy example, is going from 1 to 2, from 2 to 4, from 4 to 3, and from 3 to 1, right? Which gives us a cycle of length 7. And we see that there is another cycle of length 7, and essentially this is the same cycle but traversed in another direction. So since here we have a non-directed graph, so every cycle will appear twice in our recursive tree. Okay, and now comes the idea of pruning the search tree, and this is actually the essence of the branch and bound technique. Let's do the following. Let's construct this recursion tree just node by node. Okay, so we start at node number 0. So when we just stay at node number 1, I'm sorry, when we just stay at node number 1, so the length of the current subpath is equal to 0 because we haven't yet traversed any edge. Then from node number 1 we can go to node number 2, and at this point the length of the current path is equal to 1 because we already traversed this edge of length 1. Okay, from 2 we go to 3, and the length of the current path is equal to 6. So this is just because this is just 1 plus 5. So we update the length of the current subpath. Finally, from 3, the only available vertex, the only available node is 4, so we go to 4 and then we return back to 1, and then we save the information that we already see in the cycle, a cycle of length 19. Okay, so we save it in a variable called something like best so far. So this is a very useful information, and we will use it in order to cut some of the branches in our tree. Now let's get back to the nearest node where there was some choice, and this is this node actually, because from 2 we might as well go to the node 4. So let's try to go to the node 4. So this gives us a subpath. So this subpath in the initial graph, it corresponds to this one, and it has length 3. Okay, from 4 we go to 3, and then we have no choice again, so we return back to the node 1, and now we see that this leads us to a better cycle of length 7, and we save it in our variable best so far. Okay, this actually means that if we are extending some path and we see that its length is already greater than 7, then there is just no sense in extending it further, right? Because we already have a cycle of length 7 and we are interested in a shorter such cycle. So let's get back to where we started, and let's try from the first node to go to the third node. Okay, we go from 1 to 3, then we go from 3 to 2, then from 2 to 4, and now we see that this path is already too long. So there is no sense in extending it, but actually we do not save anything at this point because, well, we already traversed all the nodes. But then let's consider what happens in another branch. Well, in another branch we again find this cycle of length 7, but then in the final branch, if from the first node we go to the fourth node, then we see that in this case there is no sense of like extending further this subtree, because already going from 0 to the node 4 gives us a path which is longer than the best cycle that we've seen so far, right? So definitely if we use this very heavy edge, we are not going to extend it to a cycle which is going to be shorter than 7, right? So using this very simple idea, we were able to cut some of the branches. So for this toy example, the savings are modest, of course, but when the graph is larger and there is a larger deviation in the edge weights, the savings might be very dramatic. Okay? So once again, what we used to lower bound the length of the cycles that we can get in the current branch is almost something trivial, right? So we used the following fact: if the length of the current subpath is too long, then it is definitely cannot be extended to something which is better than the optimal one, right? If it is already longer than optimal, then by adding some edges would not make it less than optimal, right? And this is basically the whole approach is used in some of the very efficient state-of-the-art TSP solvers. However, the heuristics, so the methods for lower bounding all the extensions of the current path used in these solvers are much trickier. Let me just mention two of such methods which are still simple enough, and in practice much more complicated things are used. So imagine that we would like to, we have a graph and we would like to compute quickly some lower bound on the length of the optimal TSP cycle in this graph. So the first approach tells us that we can compute the following quantity. So for every node in this graph, we take two edges, two incident edges. Assume for simplicity that the graph is undirected. Then we just take two edges of minimum weight that are adjacent to this node. So we compute the sum of all such edges for all the nodes, and we take 1/2 of them. So I claim that this gives us a lower bound for the optimum TSP cycle. So why is that? Well, just because in a cycle, in a TSP cycle, for every node, we have to use two adjacent edges. For example, for this node, we use this edge and this edge. Okay? Right? So for every node, we need to use two adjacent edges, and the sum of the weights of these two adjacent edges are definitely at least the sum of the of two minimum weight edges adjacent to this node, right? So this is a clear lower bound. So the only thing that should be clarified is that why we have this 1/2 here. This is just because when computing all these minimum edges for all the nodes, some of the edges can be computed twice. For example, this node might be the minimum adjacent edge to this node and to that node, right? And since we computed it twice, to make this lower bound to work, we need to take the half of all of the sum of all these edges. So this is a quantity that can be computed very quickly, very efficiently, and this already gives us a lower bound. Okay, so if we see that this lower bound is already greater than the best solution that we've seen so far, then we stop immediately and we cut the current branch. Okay, so another way of lower bounding the cycle, the optimum cycle, is the following. So assume that we have a graph and we construct an the minimum spanning tree in this graph, and assume that the graph is undirected also. Then what I claim is that the weight of this minimum spanning tree is at most the weight of the traveling salesman person cycle. Why is that? Well, again, let's consider an optimal traveling salesman person cycle. So this is, let me just denote its weight just by TSP. Now let me do the following. Let me just remove some edge. Okay? Then what we know is that since all the edge weights are non-negative, we know that what is left has weight smaller than the traveling salesman person cycle. And also, as you can see from this picture, what we get is some spanning tree. Okay, so this is just a path, but this is a special case of a tree. It spans all the nodes and it has n-1 edges. So what we know is that TSP is at least the weight of this particular tree, right? And this tree, this is a tree. This is a spanning tree. Okay, let me write it. Spanning tree. And the weight of this spanning tree is definitely at least the weight of the minimum spanning tree, because the weight of the minimum spanning tree is the smallest one, right? And this finally proves that the weight of the optimal TSP cycle is at least the weight of the minimum spanning tree. And as you probably remember, the minimum spanning tree can be computed very efficiently, almost in linear time. So it is quite easy to compute minimum spanning tree, I mean, even for graphs with thousands of edges. Okay, so it can be computed just in a greedy fashion. We keep taking edges one by one, starting from the lightest one. Okay. Okay, now let me summarize. So the branch and bound technique, so it consists actually of two methods. The first one is how we enumerate all the nodes all the nodes that are going to be visited after the current one. In our example, we consider it just some random order. When implementing this idea, it makes sense to stick to some particular heuristic. For example, a reasonable choice of like going to the next node is to go to the nearest next node. So if we went from 1 to 2 and then we are choosing the next node to go, then it makes sense to start probably not with the node number 3 but with the node number 5 if the edge from 2 to 5 is shorter than the edge from 2 to 3. So it makes sense to enumerate nodes to visit the next nodes in order of the increasing distance from the current node. Okay? The next heuristic used inside a branch and bound algorithm is how we lower bound the cycle in the remaining graph. Okay, so we've used in our toy example, we used a very simple one, and then we've discussed two slightly more complicated ways of measuring. From this way of measuring, we need the following two things. First, it is efficiently computable. Okay, we would like to compute this lower bound very quickly. And on the other hand, it should be a lower bound. It should be a quantity such that the travel and salesman person cycle is at least this quantity. Okay, so as we've discussed already, this is guaranteed to find an optimal solution because we're essentially enumerating all possible cycles and we cut only the branches where we're absolutely sure that there is no optimal cycle, because the cycles that we're going to find in this branch is definitely longer than some cycles that we've seen before. Okay, so the running time of this idea actually depends on the instance itself and the two heuristic used. So the smarter are the heuristic, the better is the running time usually. At the same time, if the heuristic works, if the heuristic of lower bounding, for example, is too slow, this can be a trade-off. So sometimes the heuristic gives a good lower bound, but it works, but it is too slow, for example. So there is some trade-off. Okay, so finally let me mention this is exactly the idea that is used in modern TCP solvers that are actually able to solve instances of the travel and salesman person problem consisting of thousands of nodes. We now consider another technique for solving TSP exactly. It is called dynamic programming. In contrast to the branch and bound method, the running time of the dynamic programming solution that we are going to design actually depends only on the number of nodes in the input graph, but not on the structure or not on some heuristic used. So its running time is always 2 to the n times n squared. Okay? So first of all, the dynamic programming itself is probably the most powerful algorithmic paradigm. Usually the rough idea of this method is the following. Given some instance of a problem, instead of solving this problem, just try to break it into small sub-problems. Probably not to independent pieces, but into some collection of smaller problems. And then try to solve them one by one, always using the solutions to previous sub-problems, and finally reaching the initial problem. Okay? So another technical trick of dynamic programming solutions is that usually the solutions to all sub-problems are stored in some data structure. Usually it is called a table. So this is done in order to avoid recomputing the same thing again and again. Okay? So what is a reasonable sub-problem for the case of the travel and salesman problem? Well, it is actually suggested just by the branch and bound techniques that we just considered. So when we are trying to construct a cycle, what we do actually is we construct some subpath of a cycle, right? Some initial parts. So we start with some initial vertex, we end at some point, and we already constructed something. So let's then define a sub-problem as follows. First of all, assume that our nodes are indexed from 0 to n minus 1. So we have n nodes and they are numbered from 0 to n minus 1. Assume also that we always start our cycle at node 0. Okay, so we can assume this without loss of generality, because we can select any node to be the starting node of our cycle. Then and assume that S is some subset of our nodes. Okay, and I is some element of this subset. We assume also that S contains the node 0 itself. Then let's define the function C as follows. C of IS is equal to the length of an optimal path that starts at the node 0, then visits all the nodes from the set S and ends in the node I. Okay, so it looks as follows. In the graph it would look as follows. We started in the node 0, then we go to some nodes and some other node and some other node and some other node, and finally we end up in the node I, and S actually is the set of all visited nodes. So S contains this vertex, that one, that one, that one, that one, and that one, and so on. Okay, so this is just a definition of a function, and it will turn out that computing this function for various S one by one will allow us to solve the initial problem of finding the optimal cycle in the input graph. What we're going to do roughly is to compute this function by gradually increasing the size of S. So initially S is going to consist of just 1 or 2 nodes or 3 nodes. Definitely when we need to visit just 1 or 2 or 3 nodes, the problem is much easier than for visiting all n nodes. And then we will gradually increase the size of S until it reaches until S becomes equal to the set of all nodes of our input graph. Okay, so this is the main idea, but we will now, of course, extend it and fulfill all the details. Okay, so there are 2 corner cases. When I is equal to 0 and S consists of just 0, so this 0 in curly braces corresponds to the set whose single element is just the node 0. So in this case it is equal to 0. So this just corresponds to the fact that if we start in the node 0 and we do not need to visit any other nodes, then we do not need to traverse any edges, and in this case it is equal to 0. Okay. On the other hand, if I is equal to 0 but S, the size of S, is greater than 1, then the corresponding value is plus infinity. This just corresponds to the fact that it is in fact forbidden, because we C of 0S is actually the length of a path that starts at 0 but also ends at the node 0, but we are allowed to visit every node just once. So this is just some corner case, and we define it as plus infinity just for convenience. It will be needed in our code. Okay. Now, probably the most important part of any dynamic programming solution is the recurrence relation for subproblems. Okay. So remember what we need to find. So we need to compute C of IS. Now what we would like to do is to write the so-called recurrence relation for the function C of IS. So we are going to express C of IS through the values of C of some other values and some other subsets. So we're going to relate C of IS to values of the same function for probably smaller sized sets S. Okay, so what is C of IS? This is the length of an optimal path starting from 0, visiting all nodes from the set S and ending in a node I. Right? Now let's do the following. Let's consider the the second to last node on this path. Okay, so I assume that we start from 0, we visit all the nodes S, and this is I, and this is the previous node on this optimal path. So I assume that this path is optimal, which means that its length is equal to C of IS. Okay, and the J is some unknown node that is the second to last node on this path. So the question is, what can be said about this path going from 0 to S? First of all, it visits almost all the nodes of the initial path, except for the node I. So this is S minus I. So we subtract from S a one element subset containing I. So everything except for I. And what is even more important is that this particular subpath must be an optimal such path. Right? So it must be a shortest path starting from 0 and ending at J and visiting all nodes except for S minus I. This is just because our initial path was optimal, is optimal, right? Because if there was some other shorter path that visits all the edges from S minus I and ends in J, then the initial path would not be optimal. Okay? So the only problem is that we actually don't know the value of J, right? For an optimal path starting from 0 and ending in I, there could be several potential values for J. But that's issue is going to be solved in an easy fashion. So we are going just to enumerate all possibilities for J. And this finally brings us to the following recurrence relation. So C of IS is equal to the minimum over all J that belong to S and that are not equal to I, okay, over the following quantity, over the following sum, So it is C of J S minus I. So this is the same as starting at 0, visiting all nodes in S except for I and ending at J, and then traversing the edge GI. Okay, this is what we pay for the last step. Okay, and we just take the minimum such value, and this is the value of C of IS. And why is that? Well, again, just because if we have a path starting at 0 and ending at I and going through all the through all the nodes of S, then if we consider its second to last node J, then we are sure that this prefix is optimal, namely that its length is equal to this one, and the weight of the last edge, we know this, it is equal to W of GI. So the length of this path is equal to this sum. And this is a recurrence relation, and this is the heart actually of our dynamic programming solution. So in the next video we are going to discuss some implementation remarks, and then we will finally write down the code based on this dynamic programming idea. Before writing down the actual code of the resulting algorithm, let's discuss the following important implementation remark. Recall that in our code we are going to iterate through all subsets of our n nodes, right? And at this point it is important to discuss how we are going to do this, right? So once again, our goal is to iterate through all possible subsets. So first of all, the number of such subsets is actually 2 to the n. Recall that when we have a set of size n, it can be actually specified just by by n zeros and ones, right? So we can write down like an array, just a sequence like this. And if we have n elements, say, let's start them with 0, 1, 0, 0, 1, 2, and so on, and minus 1. So any subset can be specified just with a 0, 1 array. So for example, an array like this contains elements 1, 2, and so on, probably n minus 1, but does not contain the element 0 because the corresponding cell here is equal to 0. Right? So just each cell actually indicates whether the corresponding element appears in our set or not. And since there are exactly 2 choices for each cell, so either 0 or 1, the number of subsets is 2 to the n. Right? On the other hand, such a binary representation can be considered as a binary representation of some integer. Okay, so there is actually a one-to-one correspondence between all subsets of the set of size n, of the set consisting of element 0, 1, 2, and so on, and minus 1, and all binary representations of numbers from 0 to 2 to the n minus 1. Namely, so to get this correspondence, we can do the following. So to get from number k the corresponding set, we write down the number k in binary. So we write it down something like this. It is 0, 1, 0, 1, 1, 0, 1. So recall that this is the least significant bit and this is the most significant bit. And then we treat this sequence of zeros and ones as like this zeros and ones as indicators of whether the corresponding element is present in our set or not. So for example, this corresponds, recall that this is the least significant bit and its index is 0. The index of this element is 1, the index of this element is 2, and so on. So what is written here is a set that contains elements 0, 2, 3, 4, and 6, but does not contain elements 5 and 1. Right? Let me also illustrate this on an example. So assume that n is equal to 3. Okay? So we are considering all subsets of the set consisting of 3 elements, 0, 1, and 2. Okay? Then if we write down the value 0 in binary, we get 0, 0, 0. Okay? So assume that we always consider like sequences of zeros and ones of length exactly 3. Okay? Of length n. So we don't have just 1 0, we have n zeros. So we always append leading zeros so that the length is equal to 3. Then this corresponds just to the empty set, right? Just because there are only zeros here. Then if we consider 1, this is in binary, it is 0, 0, 1, right? And this corresponds to the set consisting of a single element 0. Okay? Once again, recall that when we write down these bits, so this bit corresponds to the position 0, this bit corresponds to the position 1, and this bit corresponds to position 2. So we number bit positions from right to left, right? So this is the least significant bit, this is the most significant bit. Okay? Then if we consider, for example, the value 5, when k is equal to 5, in binary it is represented as 1 and 1 because it is just 1 plus 4, right? And this corresponds to the fact that 0 is taken and 2 is taken, but 1 is not taken. So this corresponds to the subset 0, 2. So when this is convenient, because in programming languages usually working with integers is particularly easy. So it is convenient instead of working with sets to work with integers. And we've just established this nice one-to-one correspondence between integers in the range from 0 to 2 to the n minus 1 and all subsets of size, now all subsets of a set of size n. Okay? Now recall that we do not only need to iterate through all subsets, but we also need to figure out how to perform the following operation. When we have a subset S, we need to find out how to subtract some element j from it. Namely, if we just have an integer k which represents the set S, we need to somehow find a representation of the set S minus j. Okay? So assume that S represents the set, that K represents the set S. So what does it actually mean? It means that if we write our number K in binary, so here we have J and so on n. So we write it in binary, somehow it looks like this and so on. Here we have 1 and here we have something. So what we need to do, so this is K in binary. To subtract j from the set S, we actually need to replace this 1 with 0, right? So we need to flip the j's bit of the number k. So we need to figure out how to flip the jth bit of the given integer k. Okay? So this is what we've just realized. Okay, but when we have a number, if we have a number in binary something like this, so it has 1 in j's position, and we would like to flip it, this is actually the same as computing the bitwise parity or the bitwise XOR with the following number. So it has 0 everywhere except for the j's position. Okay, so if we compute the bitwise parity means that for every position we just compute the sum modulo 2. So we will have 1 here, 0 here, 1 here, and so on. So all the bits are going to stay the same as in the initial number. However, the jth bit is going to be flipped from 1 to 0. Just because 1 plus 1 is equal to 0 modulo 2. And this sign is the same as parity operation or XOR operation. It is just computing the sum modulo 2. So what we need to do is to compute the bitwise parity of our number k and the number which has 1 only in the j's position. Okay? And it is not difficult to see that this number corresponds to the number 2 to the j. Okay? Well, indeed, this 1 in j's position means that the decimal number corresponding to this binary number here is just the sum of 2j, is just equal to 2 to the j, right? Okay, now let's write this down. So in order to flip the j's bit, we need to compute the bitwise XOR of k and 2 to the j. And finally, this is how it can be done. So in popular languages like C++, Java or Python, to flip the jth bit of k from 0 to 1, we need to compute the following strange thing. So let me try to parse what is written here. So this is called a binary shift to the left. So this can be understood as follows. So we take the number 1 and we shift it to the left by j positions. So what we get is actually a number like this. So it is a j's position, and here we have j zeros. Okay, and then so this operator is called a binary shift. And once again, if you just compute 1 and apply this operator to j, then it actually computes the number 2 to the j. For example, you can check what is going to be printed if you print something like 1 to the 2 to the 10. So it is going to print 1024 because this is nothing else as 2 to the power 10. Okay? And then finally, this sign computes the bitwise parity. So this operation k and then bitwise XOR with 1 shifted to j positions to the left corresponds exactly to the decimal representation of a set S where the element j is removed. Okay, we are now completely ready to write down the code, and this is exactly what we're going to do in the next video. We are now ready to write down the Python code for the algorithm that we've just discussed. Okay, so the method is called DP, which stands for the dynamic programming, of course. So its input is just a graph, and the first thing is that we store in the variable n the number of nodes in our graph. In the second line, we create a two-dimensional table. So its rows are indexed with integers from 0 to n minus 1. Okay? Its columns are indexed with all the numbers from 0 to 2 to the n minus 1. Why is that? Well, this notation 1 shifted to the n positions to the left is exactly 2 to the n. So what happens in this line is that we create a table like this. So for example, for n equal to 3, it is going to look as follows. So its its rows are indexed with 0, 1 and 2. Its columns are indexed with numbers starting from 0 and ending with 7. Okay, so and initially it is filled in with plus infinity. In Python there is this convenient way of using infinity. So it is just float of inf. So it is a number which is greater than any other number. Okay, so initially we have infinities in all the cells of our table. And how are we going to use this table? Well, in a position, so this is table T, in a cell T of I, K, we are going to store the value of the function C of I, S, where S is the set corresponding to the integer K. So recall that S is the set of all elements that have non-zero bits in the binary representation of K. Okay? Okay, the next line. In the next line we assign the value 0 to the cell T of 0, 1, namely to this particular cell. So we put 0 in this cell. So what does it mean? This actually just means, this just reflects the fact that C of 0 and the set consisting of just the element 0 is equal to 0. So the set consisting of just an element 0. So recall that that the corresponding number is 1, because this is just a number whose binary representation has zeros everywhere except in the zeros position, right? And this is 1 in decimal representation. And this just reflects the fact that if we need to start in the node 0 and then to visit only the node 0 and no other nodes, then we do not need to pay anything. So it is just equal to 0. Okay? Then what is happening in the next line is that we range through all sets, through all numbers S, starting from 0 and ending with 2 to the n minus 1. So once again, this is just 2 to the n. And recall that in Python, the right boundary of the range is exclusive, right? So we range from starting from 0 to 2 to the n minus 1, okay? So at each iteration of this loop, we are going to compute C of IS for a set S, which is specified by small s, by small letter s, by small variable s in our code. Okay, so first of all, we need to compute it only when the size of S is greater than 1 and only when S itself contains the element 0. Okay, and this is exactly what we check in this line. So this expression actually computes the sum of all the bits of the number S. Okay, so we write down S in binary and then again we use these bit tricks in order to compute the sum of all its bits. So we range, the variable j here is used to range through all possible bit positions in S. So j ranges through, from 0 to n minus 1. For each particular j we do the following. We first shift S to j positions to the right. Namely, we kind of forget the last positions. So after this shift to the right, the j's bit becomes the least significant bit of the resulting number. Okay? Then what this operation does, so this is a bitwise AND or bitwise conjunction with 1. It actually computes the bitwise conjunction with the number with the number 1. So what happens is that we take the number S, which looks like this, for example, and assume that this one is the j's position. Then when we shift it to j positions to the right, when we apply this operand, okay, so what we get is a number like 1, 0, 1. So these numbers are these bits disappear, and the j's position is now the least significant bit. Okay, and then we compute a bitwise AND with the following number. It is just 1, so it is just 0, 0, 1. And when we compute the bitwise AND, we essentially replace all the bits with 0 except for the last one. So what we get is 0, 0, 1. So all the bits here are going to be equal to 0, and the only bit that has chances to be non-zero is the last one. So this actually just checks whether the jth bit of S is equal to 1. This is exactly what we need. And then we compute the sum of all such bits over all possible bit positions. So it just computes the size of the set S capital, right? Okay, so at this point we've checked this condition, and then we also check whether 0 is present in S. So for this we just check whether S bitwise AND with 1 is equal to 1. So we just check whether the last bit of S is equal to 1. So if the sum is smaller than 1, or if 0 is not in S, we just continue. We are not interested in such a subset S, right? If, on the other hand, so the size of S is greater than 1, I'm sorry, and if 0 is present in S, we continue. Then we range, in another for loop, I ranges from 1 to n. So we are not interested in I equal to 0, and for this reason the range here is from 1 to n. Then first we check if I is not present in S. Here, if I is not present in S, we just continue. We are not interested in such sets, right? Recall that I should belong to S. Then we start another for loop. So here j ranges from 0 to n minus 1. And again we check. So we do not need to do anything if j is equal to I, or if j is not present in S, right? So we just continue the for loop in this case. So when we reach this position, we know that S is a set satisfying these two properties. So S is a set of size at least 1, such that I is in S, 0 is in S, and j is not equal to I. So j is a good candidate to be the second to last node on an optimal path that starts at 0, ends at I, and visits all the nodes from the set S. And at this point we just try to improve the current value stored in TIS. Okay, namely we check whether this expression is smaller than the current value of TIS. And if it is smaller, then we store it in TIS. And recall that this is nothing else as C of j and S minus I, right? Because this is T of j, and this is exactly S with the element I removed from the set S. And what we need to add to this expression is the weight of the edge from I to j, okay? Namely, for directed graphs, actually we need to add an edge from j to I. So at this point we assume that our graph is undirected, okay? So this way we fill in all the table. We replace some of the plus infinities with actual values in our graph. And then what remains to be done is to return the actual result. And the result in this case can be computed as follows. So this is just the last line of our code. So recall that our function C of IS, it always computes the length of some path, starting at 0, ending at I, and visiting all the nodes. So first of all, we need to visit all the nodes. And the second thing is that we need to return back to the initial vertex. So we check all the values T of I, where I ranges through all possible values from 1 to n. So I ranges through all possible ending vertices of our cycle. And here we use the set that contains all the elements. We need a number which has 1 at every positions. at every position, okay? And to compute such a number, we just take 2 to the n and subtract 1. This is exactly the number which has 1 at 0 position, 1 at 1 at the first position, 1 at second position, and so on. So this is just a number whose binary representation is the following one, okay? So we check all such values, and for every such path, we add just the last the weight of the edge from 0 to I. Okay, so once again, this is a path, this is the optimal weight of a path that starts at 0, visits all the nodes, and ends at the node I, and then we need to add one more edge going from I to 0. And this is exactly what is done here at the last step. Okay? This is a messy picture, but this just reflects the fact that this is a non-trivial algorithm. And also its implementation here uses some non-standard, probably not so standard bit tricks. But let me finally summarize. So the running time of this algorithm is n squared times 2 to the n, because we actually have 3 nested loops. The outer loop ranges through all small s going from 0 to 2 to the n minus 1. So for this reason we have 2 to the n term. Then I ranges from 1 to n, and j ranges also from 0 to n, and that's why we have n squared term. So it is much better than n factorial. So n squared 2 to the n grows slower than n factorial. So sometimes this approach is better than branch and bound, but sometimes branch and bound is better than dynamic programming. So 2 to the n, and this approach is definitely faster than going through all possible permutations, because going through all possible permutations is n factorial. But still, unfortunately, this approach is too slow already for n equal to 20. Okay, so this approach just allows us to solve in practice instances consisting of, say, 15 nodes, depending on the actual implementation. So while going through all permutations is too slow already for n equal to 15, this one is okay for n equal to, say, 15 or 14. Okay, so this is faster than n factorial, but for practical applications this is unfortunately still too slow. So in practice, much more often the branch and bound technique is used with some smart usage of heuristics. As we've discussed in the previous videos, the exact solutions that we currently have for the travel and salesman problem do not guarantee us any polynomial running time. So we currently do not have any algorithm that is guaranteed to produce an optimal solution in polynomial time, say in n squared or n cubed or even n to the power 100. Okay, so what we're going to do in this case is we're going to design an algorithm which is guaranteed to produce quickly a solution which is at least twice longer than an optimal one. Okay, such an algorithm is called two-approximate algorithm. Okay, so first of all, it is important to mention that our algorithm only works or only guarantees to find a solution which is at most twice as longer only for the metric version of the travel and salesman problem. So in this case, first of all, the graph is undirected, or the graph is symmetric, meaning that for any two vertices, for any two nodes, we have that the weight of the edge uv is equal to the weight of the edge vu. Okay, and also what is probably more important is that all the weights should satisfy the triangle inequality. Okay, so for any three nodes uv and z, the weight of the edge uv is at most the sum of the edges uz and zv. So going from u to v through the node z could not be shorter than going directly from u to v. So in particular, the Euclidean TCP is also a metric TCP. Okay, so the Euclidean distances satisfy the triangle inequality. And what we're going to do for the metric TSP is to design a very efficient algorithm that is going to produce a cycle quickly and is going to work even on instances in practice with millions of nodes but the solution is not guaranteed to be optimal. At the same time, it is guaranteed to be at most 2 times longer than an optimal one. Okay, and this is once again called an approximation algorithm. Okay, so first of all, let me remind you that for a non-directed graph, we know that that the weight of the minimum spanning tree is at most the length of the optimal traveling salesman person cycle in this graph. Okay, and this is true not only for metric graphs but for any graphs. And the reason is simple. If we consider an optimal cycle in this graph, it looks somehow like this, and then we remove some edge from this graph, for example this one, then what is left is actually some spanning tree in this graph. Why is it tree? Well, it is just a path, and the path is a special case of a tree. This is just a non-branching tree, right? This is some tree, and it is definitely, its weight is at least the weight of the minimum spanning tree. So the minimum spanning tree is the minimum one, right? So the weight of this path is at least the weight of the minimum spanning tree, which finally proves that the weight of the optimal cycle of a traveling salesman person in a graph is at least the minimum spanning tree. Okay, then we are ready to present an algorithm. So we first construct the minimum spanning tree of G. Recall that this can be done very efficiently in time, almost linear in the number of nodes and edges in the input graph. Okay, then we do the following strange trick. We double every edge in T and denote the resulting set of edges by D. Then what we see, and we will see this now on a small example, is that the resulting graph is Eulerian. So in this graph we can find an Eulerian cycle. Okay, this cycle visits all the edges that we currently have in our graph D. Then what we do is we just return a cycle that is obtained from the cycle found in D by removing all the repeated nodes. Okay, so let me explain all the details of this algorithm as usual on a toy example. So assume that we have several points on the plane, and the edges between these points are just distances between them on a plane. So this is definitely a metric case. Okay, so we first construct the minimum spanning tree. So in this particular case, it looks somehow like this, right? Then we double every edge. So this is a very simple operation. So we just replace every edge with 2 copies of the same edge, and we assume that every such edge just has the same length, right? So they are shown like this only for visualizing that they are indeed double, right? And now what we see here is that the degree of every node here is even, right? Which means that the resulting graph is Eulerian. There is a cycle that visits every edge, not every node, but every edge exactly once. And we can easily find such a cycle. We can either construct an Eulerian cycle, and for these double trees, this is particularly easy actually, because we can kind of like hang it we can use one of the vertices as the root, and then we recursively first traverse one subtree, then the second subtree, then the third one, and so on. In any case, we can construct an Eulerian cycle in a graph somehow, and it can be done very efficiently. Let's consider one such cycle. So for example, we first go here, then here, then here, then here, here, and so on. So we finally traverse all the edges in our graph. And then we do a very simple operation. So we assume that we now need to transform this cycle into a cycle that visits every node exactly once. Okay, currently it visits some of the nodes more than once. Then we do the following. Let me use a different color for them. So we first go to this node, then we go to this node, following our Eulerian cycle, then we go to this node, then we go to this node. Then our Eulerian cycle, using the edge number 5, returns to this node that we already visited. So in order to bypass this, we do not return here, but we return we go to the next vertex. So instead of going using edges 5 and 6, we go directly from here to here. And the nice property is that our graph is metric, which means that going directly from this node to this node can only shorten our current cycle. So using this edge instead of edges 5 and 6 can only decrease the length of our current cycle. And then we repeat doing the following things. So we follow the edge 7, then we follow the edge 8, then we follow the edge 9, and then we need to and then our Eulerian cycle returns to a node that we visited already, then to this node, to that node, to that node. So we skip all these nodes and we return just directly to the initial node, right? So what we get as a result is a cycle like this one, okay? And we've almost proved already that this algorithm is too approximate. Let's now state this formally. So the algorithm is too approximate, and once again this means that it is guaranteed to return a solution which is at most twice longer than an optimal one. And it is also very efficient. It works in time almost linear in the size of our graph. Okay, because finding an Eulerian cycle can be done in linear time, and finding the minimum spanning tree can also be done almost in linear time. In time, something like E log V. Okay? So now let's prove. So we already know that the weight of the minimum spanning tree is at most the weight of the optimum solution, which means that when we double every edge of our graph, we get the set of edges whose total weight is at most 2 times optimum. Okay, and at the last stage, of our algorithm, we do some bypasses of our cycle. And since our instance is metric, we can only shorten the length of our cycle at this point. Okay, which finally proves that this algorithm is too approximate. Okay. Now, as a concluding remark, let me mention that this algorithm can be actually improved to give a guarantee of 1.5. This is known as a Christofides algorithm. So in this algorithm, instead of doubling every edge, we actually find a perfect matching on edges of odd degree in this tree, and then we actually repeat the same procedure. Okay, so a better approximation factor is known. This factor is 1.5, and it is actually the best one. So it was presented by Christofides in something like 77, so many years ago, and it has not been improved since then. Okay, let me also mention another interesting fact. So assuming that P is not equal to NP, assuming that for the general version of the travel and salesman person, there is no algorithm that guarantees an approximation alpha for any constant alpha, and even not constant alpha. So for the general version of TSP, we currently do not have any hopes for getting good approximations. Roughly this happens because if we had such an approximation algorithm, then we would be able to solve the Hamiltonian cycle problem also in polynomial time. But this would mean that P is equal to NP. The last approach that we're going to consider in this project is called the local search approach. Its main idea is quite simple. So we start with some solution, and by a solution I mean just any cycle in our graph. And we also fix at the beginning some integer parameter d. And then we keep repeating the following. While it is possible to locally improve our solution, and by saying to locally improve our solution, I mean the following. We take our cycle with n edges, we remove some n edges from it, some d edges, from it. This creates some nodes of degree 1, and then we try to connect these 2d nodes in a different manner. If it is possible to do this and to improve our solution S and to get some solution S prime, then we just replace S with S prime and continue this while loop. And we stop when it is not possible. Okay? So this is a reasonable algorithm. So What is clear about it is that it returns some locally optimum solution. So at least we are sure that when we return some solution, then it is at least not possible to fix it, to improve it by changing some D edges. At the same time, there is no guarantee, of course, whether this solution is globally optimum or not. This only means that by changing D edges in it, we cannot improve it, right? And there is, at the same time, if it is not possible to improve it with, for example, with d equal to 2, then probably it is possible to improve it with d equal to 3, okay? We will see such an example in a minute. So by increasing d, we actually increase our chances, of finding a globally optimum solution. At the same time, we also increase the running time of a single iteration of our procedure, just because when d, for example, is equal to 2, we need to iterate through all possible pairs of edges, and for any such pair of our current cycle, for any such pair, we need to check whether it is possible to remove it and then to connect these nodes in a different fashion to improve it. But when d is equal to 3, we need to go through all possible triples of such edges. So from n squared possible pairs of edges, we go to n cubed possible triples of edges, and so on. Okay, now let me show you an example. So assume that we have a solution like this. It is clearly suboptimal, right? Because it would be much better to use just only vertical and horizontal edges. And we can fix it just by changing two edges. Namely, let's remove these two edges. So we remove them and we add two new edges. And this is definitely this definitely gives a better cycle. So sometimes even when d is equal to 2, it is possible to fix the solution, to improve it. Okay. At the same time, there are cases when d equal to 2 is not enough, and this is one of such cases. Because in this case, clearly it doesn't make any sense to visit this point through these two guys, right? So to fix this solution, we would need actually to change three edges. So we would need to remove these three edges, okay? And instead of them, add the following three edges. So we can fix this solution, so our algorithm can realize that this solution is suboptimal if d is equal to 3. But unfortunately, it is not possible to realize it when d is equal to 2. Okay? So we can fix it when d is equal to 3, and we cannot when d is equal to 2. Okay? So once again, there is a trade-off between the quality of this solution, the quality of the returned solution, and the running time of a single iteration. So what does it mean is that when we increase d, we increase the running time of an iteration, because because we need to consider many more possibilities for d edges. At the same time, we also increase our chances of being able to fix a current solution. Okay? At the same time, even for reasonable choices of d, it is still not excluded that the number of iterations of the while loop is going to be exponential, but the resulting solution is going to be poor, unfortunately. This is like bad news. So there are bad examples for this local search algorithm. At the same time, this algorithm again is known to work well in practice. So practical experiments actually reveal that for many practical instances, this algorithm works quite well. And also in practice, more complicated versions of local search are known, where sometimes we do allow not to decrease the weight of the current cycle, but sometimes, occasionally, to increase the weight of the given cycle. Okay, the approach is called simulated annealing. Okay, now time to summarize. So what we considered in this project are basically two types of algorithms. The first category is exact algorithms, and the second one is approximation algorithms. So in exact algorithms, so the most naive approach is to go through all possible candidate solutions. It is called brute force, its running time is roughly n factorial, and it is catastrophically slow. already for n equal to 10, it is not going to work on your laptop. Okay, then the next algorithm that we considered, the next exact algorithm is called branch and bound. This can be considered also as a pruned search tree. So we try to extend the current permutation or the current path, but each time when we realize that it cannot already be extended to an optimal solution, we stop immediately, we stop this branch. So this algorithm, it depends on heuristic used for branching and for bounding a solution, and in practice it works quite well. So its running time is still, so there are no guarantees for its running time, but in practice it works quite well. Okay, sometimes it is as bad as n factorial, but sometimes it is much better. And then finally we consider it a dynamic programming solution, whose running time is just n squared times 2 to the n. So this allows to solve instances of sizes up to 15 or 18, depending on the programming language and depending on the implementation. Okay, and again, all these three algorithms always return an optimal solution. The only issue is the running time. Okay, and then we consider it approximation algorithm. So the first one is the nearest neighbors. So the good news about this algorithm is that it is quite efficient. Its running time is n squared, where n is the number of nodes. But unfortunately, there are no good guarantees about the solution that it returns. So we know that for general graphs, it can return a very poor solution, and for metric cases, it actually, for metric instances, it returns a solution which might be roughly log n times worse than an optimal one. Then we consider it also a minimum spanning tree-based algorithm. So for metric instances, it is guaranteed to return a solution which is only at most 2 times longer than an optimal solution. And it is also extremely efficient. So it works almost in linear time in the size of the graph. And finally, we consider it a local search algorithm, which can be considered like a customizable approximation algorithm. So it also returns a solution with no guarantees actually on the quality of the solution, but we can play with parameters to try to increase the quality of this solution. So I hope that you enjoyed our journey through this approach, and I hope that I was able to convince you that the Travelin-Salesman problem is a very important combinatorial optimization problem.